time. Just a brief summary of what we have seen so far, Shabab. We have seen the elements, if you remember, the mechanical elements. We have seen the spring element, and we say it is energy storing, so it stores energy. The equation for the linear spring and the ideal spring, we have seen ideal spring and ideal damper. And we said this ideal spring has no mass and no damping. So when we are dealing with this type of spring, so we are dealing with ideal elements. This one is also ideal. So here we assume no mass and no damping. This is just to refresh your memory. And here, no stiffness. In fact, in real life, they have this. But now we deal with them as if they are, they don't have this property. So no stiffness and no mass. And they are ideal elements. This is what we call, to simplify, simply to simplify our analysis. For the spring, it obeys Hooke's law. F is equal to Kx, where X is the deformation, whether it is any spring, it's stretched or elongated or compressed. In Laplace domain, this will be Fs is equal to K times X of S. For the rotation, same thing. We have storage, it stores energy. So the torque will be simply Kt times theta, where the deformation here is angular deformation. So this is angular deformation or angular displacement, theta. Here it's linear. This is for translation, X is for translation, and this one is for rotation. So Ts will be Kt times theta S in S domain. For the damper, we said it is dissipating energy in form of heat. So the force will be related to the velocity. F is equal to Bx dash or Bv. You will find this Bv. V is X dot. So Fs will be Bs times X of S. Here we are taking S times X of S, and it's Laplace transform of the derivative. We are taking Laplace transform of the derivative. So that's why we have Sx of S. Similarly, for rotation, we have tau will be Bt times theta dot. This is the angular velocity, or omega. Sometimes they call it omega. Sometimes you find it theta dot. So Ts in this case will be Bt times S theta of S. It is dissipating energy in terms of heat. For the mass or inertia, sometimes called mass, sometimes called inertia, for it is storing energy, we will see that it stores kinetic energy. It has half mv dot square. And this one stores a potential energy or elastic energy. We call it strain energy or elastic energy. And the force related to Newton's second law, F is equal to mx double dash. Or double dot. Here, when we take Laplace transform of both sides, provided we have zero initial conditions, we will find that m is constant, so m will stay as is, and then the differentiation of x double dash will be simply s square x of s. Similarly, for rotation, we have tau will be I theta double dot, and T of S will be I S square theta of S. This is a brief summary of what we have seen last time. Now, today, since we have the elements, we will try to find what are the laws that we are going to use to find the equation of motion or to find the mathematical model. So the mathematical model of any mechanical system can be developed by applying Newton's second law to the system. So Newton's second law, I'm sure that all of you have it, you know it. So it is just for translation. Newton's second law says the summation of all forces or the resultant of all forces is equal to mass times acceleration. This is for translation. For rotation, we can have it the same thing. Sigma moment will be equal to I theta double dot, where theta double dot, or simply this is angular acceleration. Angular acceleration. I is the mass moment of inertia, mass moment of inertia. And here we have, this is the mass, this is the acceleration, and this is the resultant of all forces. The resultant of all forces will be equal to mass times acceleration. If you remember, in dynamics, we were using this like this. If we have, we wrote sigma force is equal to mass times acceleration. Here we have our rigid body, or the body. You have the forces acting on. This is the center of mass. For translation, all the forces should pass through the center of mass. If this is F1, if this is F2, if this is F3, and F4, this is what do we mean by sigma force. So sigma force, we just write the free body diagram on the left-hand side. It will show you the summation of all forces that are acting on the system. Here, the right-hand side, we can write it like this. So this body at the end, the resultant will either move it this way. So this will be the motion of your body, mx double dash. So this is called kinetic diagram, mass times acceleration, kinetic diagram. And this one is the free body diagram. So if you look to the equation, here, this left-hand side represents all the forces acting on your system. Mass times acceleration define the kinetic diagram, how it is just one force vector, which is mx double dash, and the motion of the body itself where it is moving. So this is how do we explain this one graphically. Sigma force and then mx double dash. A rigid body, Shabab, we are dealing also with rigid body. What do we mean by rigid body, Shabab? Have you heard about this word, rigid body? Anyone knows what is by rigid body? What is rigid body, Shabab?
I think Dr. Wood don't have any deformation.
واحد, please, one by one.
And we don't have any deformation within the body itself.
تفضل رائد العقيلي.
Yeah, when all the atoms are held together, like they don't move or something like this. Yani they are not affected by the motion.
Okay, Shabab, we here what we consider that the rigid body does not deform. The internal forces interact will not deform. It will not deform. So it will be going just like this in the same manner. A small deformation. The small deformations is such that they are neglected. Small deformation and internal deflections are negligibly small, so we can neglect. So small deformation so that we can neglect them. And this is what we are seeing. When any real body is accelerated, internal elastic deflections are always present. If these internal deflections are negligibly small due to the comparing to the gross motion of the entire body, it is called rigid body, and rigid body does not deform. This is what we mean. We are going through quickly through all the laws. The guy that was sleeping under the tree, and all of a sudden the apple was falling to his head. He realized that a particle originally at rest or moving in a straight line at constant velocity will remain in this state provided the particle is not subject to unbalanced force. What does this mean, Shabab? كل الكلام. What does this mean? What does this mean, all these words? This is called the static law. The static law, or the first law. It means that we have sigma force is equal to 0. Summation of all forces acting on the body will be 0. So we have two cases. we have two cases. Case one, either the body is not moving, at all, yani at static. This is called static law, body at static is not moving. Or if you interpret this one, this is what? This is m times acceleration, or m times dv over dt, velocity. The acceleration is the rate of change of the velocity with respect to time. So either the body is at static, or case two, can somebody predict what will be the case two, Shabab? Body?
Motion without
constant motion.
Moving at constant velocity. At constant velocity. Yeah, at the constant velocity, the acceleration will be zero. So the guy is in equilibrium. The guy is in equilibrium. We call this law, we call it the first law, or the static law, or the equilibrium law, any of these things. But you have to remember, we distinguish two cases. Case one, the body is not moving at all, or it is moving at constant velocity. Is that right, Shabab?
Yes.
So the second law says if a force is acting on a rigid body through the center of mass is given a direction. Why, Shabab, here we are asking any center of mass? Why basically center of mass? And if we have forces like this, and we are emphasizing that they should pass through the center of mass. If the
because
yes, Fadal.
Anyone if it acts in another place, it will make rotation.
Okay, Shabab. So the body will be in rotation. So that's why we are assuming that they are all passing through the center of mass. So it will be translating. That's why we are assuming that this should pass through the center of mass. So with this relation, F will be proportional to alpha, yani F will be proportional to the acceleration, or A. The constant of proportionality is mass. As you can see, we said last time, we said the mass is either the quantity of substance, or it is resistance to the motion you are exerting, or to the force you are exerting. So this is the constant of proportionality, and this one is known as the second law. We can write it sigma force is equal to mass times acceleration. A is the acceleration of the body, mass is the mass of the body. The notation, either you can use a vector like this one, A, bold, or a vector with an arrow on the top of it. Similarly for the force, either bold face or an arrow on the top of it. And some textbook use this one, but our textbook doesn't use this notation. They use this one for vector also. واضح شباب? So this is the second law. And here we are writing Newton's second law in this form. We are saying the resultant of all forces, when we write Shabab sigma force, means the resultant. The resultant will be equal to mass times acceleration. A is the resulting absolute acceleration in that direction, and the line of action of the force must pass through the center of mass, so to avoid rotation as your friends. Otherwise, rotation will occur. Similarly, for rotational motion, we'll have sigma torque is equal to J times alpha. Some textbook use I times alpha. It's the same thing. Or I times theta dot. These are where alpha is the angular acceleration. So sigma T is sum of all torques acting on the given body. This will be I if you want to use I. So I is the moment of inertia of the body, and alpha is the angular acceleration. This is the second law, how we write it. The third law, I'm sure you know it. It's the law of action and reaction. If a body A is placed on the top of body B, so body A exerts a force on body A. It's written as FAB, from A to B. Body B, the reaction will be the same magnitude but opposite direction, FBA. And we write it like this: FBA is equal to minus FAB. This is the third law, or the force of action and reaction. For every action, there is an equal and opposite reaction. The torque or moment, the torque is produced of the product of a force and the perpendicular distance from a point of rotation. So the line of action of the torque will be equal, the torque will be equal force times distance, Shabab. Normally this torque, Shabab, is a vector quantity. But since here we have, this is the dot product, it's the cross product, sorry. So the angle should be 90 degrees. The angle should be 90 degrees, as you can see here. So that's why the, and the torque is perpendicular. This is perpendicular to the plane of action here, as you can see. So this is the torque here. The force is this one, and the radius, the distance, or the perpendicular distance is from here to here, and this is the force you are applying. And the torque is perpendicular to the plane here. This plane, the torque is perpendicular to it. So basically, otherwise there will be no motion. And this one, Shabab, torque is equal to, in fact, if you, the vectorial notation is force cross arm, F cross R, which is F R sine theta. And sine theta should be, maximum should be 90 degrees, perpendicular. Okay, sine theta should be 90 degrees. So we'll have the torque multiplied by the arm. If you apply with 0, there will be no motion here. It's clear. It's clear here. Torque is equal to R times F, or R cross F. This is cross product. The cross product will give you magnitude of F times magnitude of R times sine theta. So it should be 90 degrees if you want to have maximum torque in. The mass moment of inertia we'll be dealing with. Usually we will give you the mass moment of inertia because this is not one of the objectives of the course. But you should know that it is simply J is equal to the R. If you take a body, rigid body, and you take an element from this rigid body, dm here. So the mass moment of inertia will be the integral, or the integral of r squared dm, which is the distance from here to this one. This is known as the mass moment of inertia. In considering this mass moment of inertia, we assume that the rotating body is perfectly rigid, and we are dealing with rigid body. Physically, the moment of inertia of a body is a measure of the resistance of the body to the angular acceleration. Exactly like the mass, it is a resistance to the acceleration. Here, the inertia, which is written R, sometimes J, sometimes they write it I, and so on. So it is the reaction to the angular acceleration. These are some moment of inertia of common shape. We have a disk, we have a solid cylinder, we have a mass or a hollow cylinder, and so on. The parallel axis theorem. Yes, tfadal.
So, Dr. moment of inertia depends on the mass or how far we are from the.
Yeah, it depends on the mass and the center of mass, and the distance, how far you are from the center of mass. Sometimes we have also the motion, and you are applying your motion, the parallel axis theorem here. If you want, if this is, for example, the mass moment of inertia of this body here is Jg, which is about the z-axis, is Jg is given, known. So if we would like to know the mass moment of inertia about the same body, but about point A that is located here, along the z prime. So we will say Gz prime along z prime, or G about point A, will be equal to the mass moment of inertia about this point, Gj, plus md squared, plus the mass of the body. The mass of the body is this one, and d is the perpendicular distance from this point to this point, or from A to D. And this is called the parallel axis theorem. So once you know Gj, because sometimes the body is not rotating about its center of mass, is rotating about another point that is located somewhere at distance d. So we apply here, in this case, we apply what we call the parallel axis theorem. And the perpendicular distance here should be perpendicular, Shabab. The distance should be perpendicular. Like this one here. If you look to this disk here, cylinder here, the mass moment of the cylinder is simply center of mass for it in a C prime. So G center of mass or will be equal, the formula is given half m r square. Okay, so if we would like to calculate J with respect to x prime, the distance that is from here to here, J x prime. So it will be Jg plus the distance square, the m distance square, so it will be m r square. If you substitute Jg here, half m r square plus m r square, this will give you mr square plus 2 over 2 mr square. This will give you 3 over 2 mr square. واضح شباب? Is it clear?
Yes.
So شباب, here we have another example, small example. We have a bar of length L here. So J is equal to, so the length is L and the mass is M. So Jg will be simply half M L square. Can you please calculate A here? Ga will be equal to what? Ga will be equal to what? Give me what is the value of Ga? This is a bar of length L and mass M. The mass of inertia about its center of mass is 1 over 12 ml square. What will be Ga here? The mass moment of inertia about A. Can you please give me the value here? Can somebody give me the value? So if we apply this rule here, if we apply the rule here, it will be Jg plus M, the distance square, the distances will be L over 2 square. So at the end of the day, this one will be 1 over 12 ml square plus ml square over 4. And this will give you 1 over 3 ml square. So Ga, mass moment of inertia about A, will be 1 over 3 ml square. Nobody answered this question. Now, forced response and natural response. Sometimes, Shabab, we have a system. Your system could be something like this. Something like this. This is your system or your behavior. So we can have the input could be initial conditions or force. And this is your system. The output is here. This is the output. Since here in this course, we will be dealing with the system. Let me, if I try to bring another sheet, fresh sheet, or a sheet that is blank, so that I can explain on it. But I am afraid that I will scramble everything. So I will repeat the idea. Our system, no matter what, mechanical system or electrical system, we can write it in a symbolic form like this one. This is, we call it LTI. I will explain what is it. LTI system means linear time invariant system. Linear, L stands for linear. Time, and this system we are dealing with, they do not change with time. and they behave linearly, linear time invariant. يعني ما يتغير. Invariant system, they do not change with time. And if you have a mass for 5 kilogram, you come after 2 days, you will find it 5 kilogram. It will not. If you have a damper of, for example, a value that is equal to 15, you will come and find it to 15. So suppose this is our system. The system input could be initial conditions, could be a force, if we are dealing with translational system, and it could be other disturbances that we are not considering here for simplicity. So these are the input, they are called input, and this is the output. And now we are looking for the output. So our output could be either due to this initial conditions, or either due to this forcing term, or both of them. In all cases, if you would like to know the output, we take the natural response that is due to the initial conditions or only homogeneous response. Homogeneous, يعني the right hand side will be equal to 0. The homogeneous response, معناته we will consider forcing equal to 0, and then see what are the initial conditions. These are the initial conditions. So we will write down, or we will find the response, how the system behave to the response. This response, we call it homogeneous. Homogeneous. And when you study the differential equation, you are calling it homogeneous. But in fact, it is the natural response or the free response. We can use these two terms, natural response or free response. This is when we talk, when we are mechanical engineers, we use these two, free response or natural response. And we know that this response are due to the initial conditions. So this is our response here, the lower one. This is our response that is due to the initial conditions. We write it down. And then after that, we ignore the initial conditions here. We ignore the initial conditions. We assume that they are 0. And the response is responding only to the force. So this one, we call it forced response, or the force that is due to the forcing term. If you remember, when you were solving differential equations in math, you were saying that this is the particular solution, or the particular integral. And the solution will be yp. This is yp, that is due to the forcing term. And this is what you get, forced response. We add this together. We add this together, as you can see here, and we will obtain this, because this response plus this response, you will get this one. And this is the total response that is due to the forcing term and due to the homogeneous term or the initial. So forced term plus free response. The free response is due to initial condition, and the forced response is due to the forcing term. Now, when we deal with Laplace transform, take this together once, مرة واحدة. Okay, once and for all. He does not separate between this one. The initial conditions are already there. And this is the beautiful thing in Laplace transform. You don't have to carry out two integration or two solution. Just in one shot, you will do the solution that is due to the forcing term, the right-hand side, and the solution that is due to the initial conditions. Is this clear, Shabab? Forced response and natural response or free response? So this is what we have here. X, in general, the total solution will be due to the homogeneous term plus the particular solution term or the forcing term. In the presence of damping, when we have damping, Shabab, the solution, the homogeneous solution that is due, it will die after some times. It will die. And the motion with time, it will go to 0. It will die. In the presence of damping, if we have damping is there. The particular solution, it will stay. The particular solution, because it's always there, because there is a force applied on it. Now, when you superimpose the two solutions, this solution plus this solution, after some times, since the homogeneous solution, you will not see it, you will see what we call the steady state solution. And this steady state solution will be equal to the general solution that is equal to this plus this. And you will not be able to distinguish between the forcing term and the steady state term. they will be the same. لأنه الhomogeneous will disappear. This is the homogeneous dotted line. After some times, it will disappear. It will be 0. So this plus this will be equal to this one. 0 plus this one will be equal to this. And this is the general solution, or the steady state solution. We call it the steady state solution. واضح شباب؟ if you can go please through this applet, they are extremely important. I will try to give them to you now. I'm not sure if I can access them, but give me some time. Well, just 1 minute. If you give me 1 minute, I will try into this app and try to show it to you how it works. Just give me 1 minute, Shabab. Please be patient. Don't go away. Stay with us. This is our lecture today. I will try to give you this. I'm sure that some of you will not be able to get into the AIMP and then forced damped. I know this one is extremely important. Damped VIB, vibration stands for vib.html. I'll try to show you this one. If I succeed, I'm not sure, because I hope it will work with us, inshallah. It is taking more time than necessary, and the idea clear, Shabab. لأنه the presence of damping will make the motion dying after some times. When there is, of course, free vibration, يعني you give initial condition to the system and leave it for the free vibration. So what will happen in the presence of damping? It will die. There is a force always acting there. The motion will be always there, and the system will be always excited. This is the idea behind it. So I'm just trying to bring the website here. As you know, the line here in KFUPM is very slow these days. I don't know why, either from the service provider or from the network. I'm not sure. So it's taking too much time. The students who were with me in class face to face, they know what I am talking about. It takes a long time to open the net and then show you the applet, how it works. It's still not coming. I'm still waiting. You know, this policy, acceptable use policy agreement, KFUPM. I said I accept, still nothing is coming. We will come back to it because I have it here. When it comes, we will talk about it. Procedure, how do we find the equation of motion? You know it. We select suitable coordinate system, and we select the mass. We will select the static equilibrium, draw the free body diagram, we apply Newton's second law, and so on. This is how do we proceed. So for the translational displacement, this is what we have. We have a spring that is connected to a mass, and the mass is moving in this direction. This is for translation. And we have all the parameters here: linear displacement, linear velocity, linear acceleration, linear momentum, forces. For rotational motion, we have this type of displacement, angular displacement. It's coming now from the other side. Let me just pick up the right one. Try to pick up the right one here, Shabab. Okay, now this is here. Let me just bring this one here now. I will say share. I will go here and then share my application, share application. Inshallah, just pray with me. Inshallah, it will work. Do you see anything, Shabab? Do you see the anything? You see this one? You see the face here? You see this one, Shabab?
Yes.
Oh, you see the notes?
No, the desktop face.
Doctor, I think you have the window in another screen.
Yeah.
Yes, it is another screen. I just brought it here, but I don't know why it's not working.
Oh yeah, now
it's
it's
coming,
appearing.
yeah.
Yes.
Yeah.
I try to bring it, Shabab, here. شوفوا Shabab, this is what we have here now. We have a system. The green one, this is, I can play with the mass here, the damping here, and the stiffness here. I can play with this. So what do I can, if I can play with this one, see the motion here, how it is moving. See if I add the damping, how the motion is dying, slowing. So if I increase the mass, normally you should see this one. Now, if I put this force, there is no force, free response. If I take this term, no force here at all, no force. So you see the motion, how it is moving. The damping, the natural frequency, and then you can add the initial conditions here. I'll just try to fix these things just 1 minute, and you will see how things are moving. So what we are interested in, our equation is mass times acceleration plus damping times velocity plus stiffness times displacement is equal to A cosine omega t. This is the right-hand side. Now, Shabab, if we add the damping, we see the solution. I'm giving just small values for this here now, and then from here, the values from here. And then I will just reduce the mass. I will add small damping, and you will see now the stiffness. You see the stiffness, how it is moving. The values, these are the initial conditions here. I can bring them here. And then you will see the three values. The amplitude, I'm trying to bring the amplitude, small amplitude here. What is the amplitude? This.
Doctor, change the scale above so we can see it.
Scale, which scale here?
There, yeah, the upper left.
So I will leave it like this. So this is the amplitude. So this is the scale, you will see it. This is the amplitude motion. And this is the vibration. شوفوا شباب, I'm not sure if you can see the green one, three curves here. At least you see the motion, how it is moving. I'm not sure if you see the three curves. One is blue, the transient. The other one is the green. The green one.
The green isn't.
So the steady-state solution is the green one. If you, after some times, it will die. The motion will die. Let me just increase this one. I'll give values for amplitude. I will increase the damping. شوفوا شباب, if I increase the damping, you will see three: green one, yellow one, and the blue one. The blue one, all of a sudden, quickly it will die here. And the green one with the blue one, you will not distinguish them. لأنه a particular solution will be exactly the steady state solution. So transient, if I remove the steady state solution from here, this is what you will see. You will see that they are same as the total solution. So I will increase a little bit the damping. See now, Shabab, if I reduce the force, the amplitude of the force, it will be 0 because the initial conditions will be 0. See now the initial condition, and I reduce the amplitude of the force. This is what will happen because of the damping. See, Shabab, because I have damping here, this motion is free vibration. A is 0, the amplitude of vibration is 0. After sometimes it dies because I have initial conditions. This is X and this is X dot. This is because of the initial conditions, I have this one. So the solution, free vibration, is this one. Now, if I add a small amount of vibration, the amplitude, see the transient which will die. The transient is the blue one, it will die. And then from here, you will not be able to distinguish the steady state solution with the transient solution. Is it clear, Shabab? If I increase the damping, see the solution how it will be. واضح شباب? Now the mass is this one. See now the blue one is the transient. After some times, the blue one will disappear. And the green one, you will not be able to distinguish the green one with the yellow one. I remove the blue one so it will not disturb you. See, I remove the blue one. We have just green one with the yellow one, which is the solution. Is this clear, Shabab? Is this clear?
Yes, clear.
طيب, alhamdulillah. As long as you understood this one, so the steady state solution will be the final solution, which is called the. Let me go back to my notes. I hope I can get them back easily, inshallah. Just لا تضحكوا علينا شباب، احنا لسه يعني في التطوير تاع التعليم هذا عن بعد، لسه شويه
Dr.
يعني.
Justice, press the stop sharing and it will go back to the blackboard.
Okay, now we are in the blackboard back. Inshallah, let's go back to our slide. I think we have 5 minutes. If I can talk about 5 minutes, it will be great. Alhamdulillah, now I showed you what I mean. I hope and everyone understood this, the meaning of this slide. So Shabab, now if we have a problem like this one, which is about the rotational motion, in the figure here we have a disc or rotor mounted on a shaft, and it is rotating, and the shaft is fixed by bearings. You see the bearings, and then the rotation is omega and the inertia is J. If we write Newton's second law, or if we draw the free body diagram, what we will see the rotation omega is here. Omega, remember this omega is simply theta dot. In fact, it is omega is theta dot. I will use the black one today. So omega is simply theta dot. It's not coming, I don't know why. So here we have theta dot, which is equal to omega, نفس الشيء. Omega is equal to theta dot. Now the bearing or the friction on the bearing, if the motion is like this, the friction will be on the opposite direction, the friction that is due to the bearings. So it will be B omega. واضح شباب? Or B theta dot, B theta dot. If we write Newton's second law, we can say summation of all moment will be equal to J theta double dot, يعني angular acceleration. واضح شباب? Since theta double dot is simply omega dot, J omega dot, we can write Newton's second law like this. We can express the left-hand side. The left-hand side means we should introduce all the moments are there. What are the moments that are here, Shabab, in this figure? We don't have any moment except the one that is minus on the opposite direction, minus B omega equal to J omega dot or J double dot. Minus, and then here, and then here. Now, if I write this equation, I can write it like J omega dot plus B omega is equal to 0. And this is what? This is my equation of motion, the free vibration of motion for this one. Now I am taking omega, Shabab. I could take theta, or it's up to you. You can take omega as omega dot or omega. So we are seeking a solution for omega. What will be omega? Of course, there will be motion here. Even the right-hand side is 0, the free vibration. So I write few words here. This is a free motion or free vibration of the rotor. The vibration شباب هنا is due to what? To the initial conditions. يعني أنت give small rotation here, أنت give small rotation here, and this will be your initial conditions. We are saying omega 0 is equal to omega 0. A value that you give at time t is equal to 0. So it starts rotating. شوفوا شباب, if you have rotation هنا and you give small rotation بيدك كذا with your hands, just a little bit, what will happen? What do you expect will happen to the rotor? ها شباب? It will rotate maybe half turn, maybe quarter turn, maybe one turn, depending on how big you give your initial conditions, and then it will stop. Why it will stop? Because you have damping of the bearings that is due to the bearing. Now, if we look to the equation, how did we find it? We found the equation in this form: G omega dot plus B omega is equal to 0, or we can divide by J, and we write it in this form: omega dot plus B over J omega is equal to 0. Or further, we can write it like this: omega dot plus 1 over GB omega is equal to 0. Or we can say omega dot plus 1 over omega is equal to 0, and this is the initial conditions. This tau hina is called the time constant, where tau is equal to J over B is known as the time constant. I will tell you the story for the time constant, inshallah, in the next slide. But now, if we assume this is the first order system, we call it a first order system because it has the first derivative. The first derivative, this is dot, to the first derivative with respect to time, omega dot. And the free vibration because it is 0. And the motion is due to the initial conditions. These three things. We have omega dot first order. We will write it first order. And omega dot. We have 0. It is free vibration, free motion. So if this free motion is due to what? It is due to the initial conditions, omega 0. Now, if we take Laplace transform of both sides of this equation, we will find the following: omega dot Laplace transform for it will be S omega S minus omega of 0. This is the initial condition. Omega S is Laplace transform of omega. So omega S will be simply Laplace transform of omega. And then plus 1 over tau omega S. شوفوا شباب, now, if you solve for omega S, you will have omega S common here and omega S common here. You will have, so S plus 1 over tau omega S is equal to omega 0. S plus 1 over tau omega S, I will repeat in S plus 1 over tau omega S will be equal to omega 0. If you solve for omega S, you will find this equation. Omega S will be omega naught S plus 1 over tau. S plus 1 over tau here is the denominator. And the pole, if you solve this equation, you will find S is equal to minus 1 over tau, which is a pole. So the response, how omega t take the inverse Laplace transform. When you take the inverse Laplace transform of this one, you will find that omega t, can anybody tell me what is the inverse Laplace transform of this? Will be equal to omega naught exponential minus 1 over tau t. So it is decaying. The denominator here, we call it the characteristic polynomial. And if you solve this equation, you will get S is equal to minus 1 over tau. And the solution will be decaying. Decaying solution like this one. omega will be omega naught exponential minus alpha t, which is decaying. Where alpha here, I am putting it as minus 1 over tau. Minus 1 over tau. The solution is decaying. When alpha is equal to 0, this one will be constant, and the solution will be decaying like this. It's clear. The motion of the rotor, it will go to 0 quickly. Because why? Because you just give in push, little bit push, or you give a small rotation, and then you lift it. When you lift it with time, it will stop. It will go to 0. And this is the free response of the rotor. Alpha here, or B over tau, B over G, these values they will increase. Okay. Okay, Shabab, I will take the attendance. Sorry. The lab is at 3:30, Allah yarda alik. At 3:30, still you have time. Why you are just, let me just take the attendance. We will start, inshallah, from here next lecture. We will start the lecture, please. Give me just 1 minute to take the attendance. Who is with us today? I think I have 36 students. It shows that I have 36 students, but I don't know if they are here or they already left. Like some students, this is what they do. Not all of you, but some of them, they forget themselves, or they go and take some cup of tea and they don't come back. And this is not good. Bismillah ar-Rahman ar-Rahim. I will just, I'm sure that you are fine. Alhamdulillah, everything is okay. I will not ask you. Some students are in hurry. I'll just call the name. العلوة منير موجود. العلوة منير. الدرغالبي الدرغالبي شكرا. المسعودي. الملح ولا المولى ولا ماجد. ماجد. القحطاني حسين. المحمدي عبد العزيز. اليحيى عباس. يحيى عباس. عباس اليحيى. القحطاني عبد الكريم. الشهري علي. الشهري علي. he is here. الرميح هاني. الرميح ما شاء الله هاني موجود. القرني علي. قرني علي. الزهراني فارس. فارس الزهراني. الحمدان عبد العزيز.
موجود دكتور.
وسهلا. الشريدة محمد. شريدة العجمي مبارك. طليحي يوسف. الزاير حسن. الجوهني نادر. أهل النادر. العقيل رائد. رائد
موجود يا دكتور.
اهلا وسهلا. الدرويش عبد الله. اهلين درويش. شرفنا. يا رائد يوم الاثنين كنت غايب.
نعم يا دكتور، كنت غايب يوم الاثنين.
سلامات ان شاء الله. وش غير خير
الله يسلمك. الله يسلمك. لا خير، اشارات علينا يا دكتور.
اوه يلا شد حيلك. الدبيس موجود. الدبيس. البشر علي. جارودي حسن. جارودي كيف حالك؟ ما سمعت صوتك اليوم، الله يرضى عليك. الرشود. اوه يلا سلامات ان شاء الله. صلح الرشودي. سلامات ان شاء الله كله تمام. الهاشم ناصر.
حاضر دكتور الهاشم.
كيفك يا ناصر؟ ان شاء الله بخير.
تمام الله يسلمك.
العوض سلطان. يلا شباب. السوبدي علي. السوبدي موجود ما شاء الله عليه. عبد اللطيف عبد اللطيف كيفك عبد اللطيف؟ ان شاء الله بخير.
خير الله يسلمك يا دكتور.
العبد رب النبي موسى، شيخ موسى. الزهراني عبد العزيز بندر. العتيبي فهد. فهد you are in section combined now معنا حضرت؟
اي دكتور دخلتني انت في الكومنت سيكشن.
المحمدي يزيد الصبحي نايف. يلا شباب سعيدة ونشوفكم غدا إن شاء الله بإذن الله. I hope you got something new إن شاء الله. يلا شباب فرصة سعيدة بالتوفيق إن شاء الله. سلمان